about the test. Since the test is coming up, I wanted to mention, or we can kind of figure out what we'll do for the test. So Monday, unless there's some big problem with that, if somebody knows about something like the college is actually closed that day, or nobody can go for some reason, or there's a midterm in another class that everybody's in, we could do something else.
Aliens.
But aliens, yeah.
Aliens.
Yeah, so then, okay, now the calendar for this class mostly just has a bunch of entries that say we'll learn about GPU programming, like with graphics, and then later it's got a bunch that say we'll learn about GPU programming for kind of general purpose computing, and it's not very specific in this class. So that makes it a little harder to figure out what would be on the test. And then instead of a traditional textbook, we've got some tutorials leading up to this cube one we keep using, and then various supplemental resources, sometimes other tutorials, sometimes stuff at the Kronos.org wiki. And so if you go through the lecture notes and make a list of all the supplemental resources, then you have a textbook, kind of. So I made a little bit of a summary about what we talked about a lot. So we talked about, isn't there a type of shader missing? I guess not. So we talked about shaders a lot. So you want to be real familiar with what the various types of shaders do and what you would use them for. So right now, at least with OpenGL, we got 6 types of shaders, and that's why I thought that list was too short. So we got the vertex shaders, which we've been using since the very beginning, and in the fragment shaders since the beginning. Then there's the tessellation control and tessellation evaluation shaders for the more detailed versions. The main example for those would be the level of detail example, LOD on a Soptra. We've also used it for some other stuff. The seed fruit demo, for example, has a level of detail included in it. Then the geometry shaders, probably the best example for those is that lab we did with the bulging sides on the cube. That one covered geometry shaders fairly thoroughly. So those, the fragment and vertex shaders have been in everything so far. And then with the compute shaders, there's a demo with cubes, like bouncing cubes. So the top and the bottom actually bounce independently, and the bottom can go through the top. I think it's called CompShad. Anyway, there's that compute shader demo, and then, of course, seed fruit has compute shaders. Seed fruit puts a lot of this stuff together. That's what it was intended for. So yeah, we would be very familiar with those. I could have a question where it's like, you need a geometry shader that does such and such a thing, so go ahead and write one. Could have one where it's like, okay, here is your vertex shader, and then here's your fragment shader, and here's the vertices that come in, and so what's it do? What's it look like? Draw it in 3D. What we needed to have for these, and I don't have a bunch of these because I didn't think of this until today, and probably wouldn't have done this anyway. There's these 3D pens you can have, and it lets you draw stuff in 3D basically. And so this would be like perfect for this class. I'm going to turn the sound off because I want to talk and not them. I guess that's an ad. Anyway, so yeah, this would be a good way to have answers for the test. So you put all this stuff here, but it builds up layers of plastic, and so you kind of manually 3D print things. That's a little bit of a tangent. Anyway, since we can't have those, it'll limit a little bit what kind of questions can be asked on that. Yeah?
I just thought of something. Is it possible for us to have the test on Wednesday instead of Monday?
What's better about Wednesday?
I don't come off a 36-hour work week.
Oh.
I work 12 hours a day, 3 days in a row, and I've had all my finals or midterms on Monday, and I'm just so exhausted that it's hard to think.
Sure. Is there anybody that has a similar problem with Wednesday? I mean, do we just push this off to something else? Or is it no? Okay, well, I'm good with that. Because I'm one class behind after the dentistry incident, so that sounds good.
Yeah,
okay, cool. So we'll do the final on Wednesday. So that's that. Okay, but it'll still cover the same stuff. Yes, what does this do would be a pretty good question. The whole thing gets rendered onto a screen anyway, so eventually it's perfectly possible to draw it. Now, the thing about the drawing, I asked drawing questions a number of times on tests, And they're always a little bit fun. But sometimes I'll have some program and it like draws an antelope and somebody else draws a picture of a tank. And I always have trouble figuring out how to get partial credit in these cases. Anyway, might have something like that. Or here'd be a good one. I could have a geometry, or I could have a pipeline, and it's got all the pieces in it, and then a picture of what it draws. And then, if you change like one line, what's it draw then? And that makes it harder to be done that dramatically wrong. Okay, anyway, something about that stuff. I like that Wednesday anyway, because my leading candidate for when am I going to write the test was actually Sunday night. Because my tenure portfolio is due on Friday, so it's not going to happen before then. And then I'm probably going to take a break for just like Saturday. And I was going to write the test on Sunday night. Yeah, so now I can write it on like Tuesday night. Okay, GLSL. So code for this class, the test languages will be GLSL and C++. We haven't really talked about any others. I say C++, not C, because so far all of our examples have been a CPP file. That said, except for GLM, which doesn't work right with C, the entire example could be thrown into a C compiler and come out perfectly fine. So the C++ that we've been using is also within the C umbrella. But it's not a C test. So unlike operating systems, there won't be like a weird question on pointers. There might be a question that involves pointers in memory because you have to be able to copy memory off to the CPU and or GPU and whatnot. But it won't be a question like, oh yeah, you got this function, and this function takes a function as a parameter, and a function that comes into the parameter takes another function that processes lists of functions. None of that nonsense. That's operating systems class nonsense. Because I actually use that in operating systems. I really like systems programming because they use that kind of thing. It's fun. It stretches your mind. Right, with regular programming, after a while it gets boring. You get the line and does something, and the next line does something else, and so on and so forth. But with operating systems, there's always kind of a sense of awe and wonder about what a line might actually do. Okay, so yes. So essential things to remember about GLSL. Remember what you can and can't do in it. There's not that many things that you can do in C, but you can't do them in GLSL. A few that come to mind: you cannot use printf in GLSL. It's not available. You can't really do string processing or that kind of thing. You don't really get to do error messages particularly. It kind of either works or it doesn't. You can't malloc or directly manipulate pointers. But things that you can do that aren't in C, it does matrix operations natively. Same thing with vectors. And so if you say a vector plus a vector, it adds the two vectors. C doesn't do that. So there's a number of things like that. I suppose you could have an overloaded vector type in C++, since this is C++ here, and add two overloaded vectors together. But that's more a 312 topic. Okay, so that's that one. Okay, 3D and 4D matrix operations. I'm going to try to minimize these a little bit. Linear algebra is not a prereq for this course. I'm sure that some of you have it, especially those of you that are dual majoring with math. But I know not everybody has it, and I don't want to sort the grades out by who's had linear algebra and who hasn't. That seems like sort of an unfair division here. So I'll try to minimize use of that. Now, do remember what the principal matrices do here when you multiply by things. You got a model matrix and a view matrix and a projection matrix, and you multiply them all together, and you get this matrix MVP. And when you multiply by that, it takes your model and it puts it into camera space. And with lighting, we'll pick that apart a little bit, but I won't pick that apart on the midterm. Those all just come together and make that thing. Might ask something, explain what the MVP matrix is, or something like that. How do you get the MVP matrix? Or which coordinate systems does the MVP matrix translate between? It goes from the model coordinates to world coordinates to camera coordinates after that. So something like that might be good, something kind of general about it. But you probably shouldn't spend a whole lot of valuable study time studying how to take the inverse transpose of a matrix. Okay, Then 3D and 4D vector operations. I can't avoid those. They're just too critical in 3D because everything ends up using them. Because we have all these points, and the points are represented by vectors, and you can add them together and go places and whatnot. This is not quite as much a Math 340 topic. It's more of when do you learn vectors? Pre-Calc 1 or something, right? Or 2? Trig for sure, I think. Something like that.
I'm pretty sure it's calculus.
Is it?
Somewhere in calculus.
Oh, I thought it was earlier.
That was a constant thing in pre-calculus. Yeah, you'll be learning vectors next. Vectors are harder.
Oh,
No, I have a lot of repressed memories from calculus 1.
okay. I actually learned them in about 6th grade. The math textbook had vectors. And I thought they were really fascinating. I think everybody learns them in 5th or 6th grade, but unless it strikes your fancy, you just sort of forget. But I thought they were great. Anyway, okay, so yeah, 3D and 4D. So to some extent, these things. So when you normalize a vector, you just make its length 1. Remember that vectors have a direction and a magnitude, and so like a normal vector is 1 unit, and it points in a direction is perpendicular to the surface. Remember definitions like that. It's good to remember like what the dot product and cross product are, but you don't have to do one. So if you remember that with a dot product, you take the two vectors and you get a new vector. Well, you don't get a vector, you get a scalar that indicates kind of the shared magnitude. So if you got two going in the same direction, you get a large dot product. If they're perpendicular, you get a dot product of 0. And so, kind of the nature of what it is. Cross product, you take two vectors. Need vectors here, okay. I got the black vector, and I got the blue and black vector, and I got the black and red vector. So if you got two vectors like this, you take the cross product, you get a vector that's perpendicular to both of them. Could be either direction, it depends. Depends on where it is related to the two here. The important thing is you get a perpendicular one. So if you wanted to calculate a normal vector for a surface, and the surface had a triangle, and these are two sides of the triangle, you take the cross product, you'll get something that's perpendicular. Something you could potentially use for lighting calculations, as long as it's going the right way. And so that's where winding order comes in, making sure it's the right way. Okay, yeah, not a heavy emphasis on it. It's just that they do have to happen. We're just talking about how you're not going to get too much of an advantage for being a math major. So that's good. Okay, so we can have a handicap, or if you're a math major, you have to come in half an hour late.
Oh, that's great. I don't break the curve.
Okay, so yes, that's about it for 3D and 4D vectors. So for lighting, I might ask a general question about lighting, but we haven't had a lab on lighting. We actually might, now that the test is Wednesday instead of Monday. But I'll leave like a detailed lighting question off of it. I wasn't planning on asking one, just not ask one. Honestly, the lighting in this class is more of an explanation of soon-to-be how shaders work and how to solve an actual problem using shaders. It's good to know about, since we know about 3D, it's good to know about light. So it serves that purpose too. But this class is more focused on the graphics processor and how you program it than on 3D in particular. It's just that they're so tightly tied together, it almost seems like the same thing half the time. Anyway, we'll do like a super detailed one on lighting. This may be general, what's the difference between diffuse lighting and ambient lighting? Ambient lighting comes from nowhere in particular. Diffuse lighting comes from a particular direction. It's a good general question. Okay. Was it
playing a game?
Yeah.
Where you had lighting, and they had ambient lighting set by the day cycle.
Oh, really?
So when you're underground in your mind, you can still see the diffuse lighting from the day cycle. So you can tell what time it was outside of the mind.
Oh, interesting.
That's better than, you ever played the original, Pokemon Fire Red? New lighting in that game. They warmed dark.
Hey, you got it.
Down a little bit.
Oh, yeah, sounds like vacuum cleaner. So Austin is working on a prime number project, and he's got a software busy.
What are you doing?
And the
Virtual
CPUs are 65 degrees centigrade. To compare and contrast, in this room, the computer's CPUs are around 30 degrees centigrade. If you're curious what happens if you touch one at 63 degrees centigrade,
You burn yourself.
well, not too bad. It's, let me go get the exact number here, 145 Fahrenheit. And so 145 is hotter than a hot tub. Those are usually around 104, somewhere in the area 106.
It would hurt.
If you're out in the woods and you found a hot spring that was 145, it would not feel like a hot tub. But you know, boiling is like 200 and some change. And so if you touch a pot that's got boiling water in it, it would hurt worse than the CPU there. It depends how you're touching the CPU, of course. If you're touching the top of the CPU and it's covered with thermal grease, it'll be worse than if it's dry. But it's beyond comfortable for sure.
It's like a warm enough to where we can take a pan and fry an egg on it.
No. No. Not even close.
I got
They'll congeal at that temperature, but if you're cooking, setting up a frying pan for an egg, you put it much hotter.
some AMD stuff can get up to 90 degrees safely.
Yeah, this is critical's 92.
Yeah, so it's not.
Oh, look at that, it's going out for it.
Oh, it's
So
done.
basically, it's
It finished.
Yeah, it rests around the same as this one.
So if you check the first 5 million numbers, there's 348,513 numbers.
Nice.
Oh, is that all?
Maybe I should show that to my 108 class because they've been, we did a prime number test on App Inventor.
Yeah, well, this one, it doesn't multi-thread the test, it just does multiple tests at once.
Sure,
Yeah.
that makes a lot of sense. Yeah. Okay, so lighting's there. OpenGL. We'll talk about OpenGL to some extent. I am trying not to make it too tightly tied to OpenGL, but since that's the 3D programming system we've used, it'll be somewhat OpenGL specific. I'll try not to test on things that are like a really weird quirk of OpenGL. Like what is a GL float? But it's going to involve OpenGL to some extent. You got to understand how OpenGL works before the test will make any sense. It'll be on there in that sense. So the cube demo comprises pretty well the major OpenGL calls that I think would appear on the test. So if you understand the cube demo from end to end, you're doing pretty good on that. The other thing that might be on there is instance rendering, which is not in the cube demo. And so if you also understand, say, GL draw elements instance, that function, I'll put it on this one, and then it'll be on the camera. Okay. GL draw elements instance. Okay, there, this function. If you understand how this function works, that would be the thing that's not in the cube demo. And this one just takes, you get a whole bunch of instances of the vertex shader, and you can tie these to an array using the instance ID as an array index, and that way you can draw a whole bunch of stuff at once. If you are doing the grass project, it's a good way to draw the grass more efficiently than using like a for loop. For each blade of grass, draw the blade of grass. Because if you do the for each blade of grass, draw the blade of grass, and the blade of grass is like, say, 4 vertices, then you're kind of doing a sequential process involving 4 out of like 1,900 compute elements. And so it doesn't take very good advantage of the GPU. Okay. So that one too. Okay. I think that's about it. So studying. My suggestion would be understand the cube tutorial like thoroughly. Understand the examples and the labs very well. And so if you know all of these things, I think you'll probably do fine. Okay, so that should be a way to kind of focus efforts. Unless that's overly broad, in which case it's the opposite of focusing, but at least it's some way to direct. We are now going to focus on all of these 10 areas. Yeah. Yeah, so it's a focus like a floodlight. Okay, so that's the plan. Okay, and as usual, a page or 2 of notes is fine. I have this kind of sort of aspirational goal. I never quite figured out how to implement where you can somehow use the man pages for the test. Maybe sometime we just need to set up the machines with man only or something like that. I haven't designed a test that way yet. You can also buy the man pages, like for your Unix, just print it out in a book. And so one thing I've thought before for like operating systems, Linux, networking, possibly other classes, I should buy like 20 copies of the manual, print it out. I'm sure you can find it on eBay for a decent deal, and then everybody just gets to borrow one for the test. Haven't done it yet. Wouldn't help you nearly as much in this course, although I realize a lot of the OpenGL functions are in man.
Although the man page becomes slightly less useful because you're not using man anymore to read man pages.
Yeah, I can ask a question about man.
Yeah, you can.
Anyway, that's
What
it.
is man?
Yeah. Yeah. What does the pick some random option -L option do on man?
Oh.
Bonus points if I can pick one that's not actually there. Probably like nothing.
Good question.
Okay. Yes. There we go. So yes. As far as what you should put on these page or two of notes. If you've got enough space and time, I would kind of recommend go through the cube demo and then take the two instance rendering ones, GL draw arrays instanced and GL draw elements instanced, and put each of those functions along with the parameters and a brief explanation of what they do. That would be my suggestion. It'll take a little while to make it, but it'll be a good exercise because at the end you'll be more familiar with all of these things. And then you can keep it as a handy reference if it's written in more than a 3-point font. If it's written in a 3-point font, you might want to just like print it out bigger on more pages for a reference. Or keep it on, people don't print things out anymore for a reference. It used to be in the old days. So you see this keyboard here? We wouldn't like this keyboard. Here's why. The keys are too short. Since they're too short, if you take a piece of cardboard with a cutout with holes for your key pattern, it won't hold your cardboard in place very well. And so if you got a word processing suite, like leading edge word processing, it would come with a foldable, unfoldable sheet of cardboard that you lay over your keyboard, and it would have explain like what the F keys do in your product that you just bought. Yeah, they do. And so then if you were wondering like what does F6 do inside leading edge word processing, you'd have a little note right above it that explains what it does.
Now you just press the button to reap the consequences.
Yeah,
Pretty much.
And you wouldn't use this, I mean, if it was a program you used frequently, eventually you wouldn't get the cardboard thing out of your box and set it up. You'd just remember it, but it's kind of handy.
Well, I mean, and like the whole top there, it was a lot wider, like in the Model M up there.
Yeah, these days the F keys still do things. And usually it's just on the screen, like here, F5, tree. What's a tree look like? That didn't do anything. Oh yeah, it did. It's over here. Yeah, I made a tree of which process has. It should show my operating systems classes.
Yeah, that's really nice.
Cool. F10, quit. Except it's also remove frame on my window manager. And so the window manager is intercepting it. That's the problem with the F keys. Since they don't do things all that often, it's really tempting to use them for your own purposes. I never use that middle pedal in my car anyway, so I remapped it so it just blows the horn. Okay. Anyway, back to this thing. Okay, so taking apart the light demo, picking this thing apart from basic texturing. Okay, let's take a look at it first before we grab it and disassemble it and use it for our own ends. The basic texturing demo here. I showed you this on last Wednesday. Shows you this globe, and it's actually a demonstration of how to texture. If you look at our modern tutorials ebooks, okay.
Seth,
Yeah.
Can you take an input in two different places in the pipeline?
Where's the input coming from?
If
If it's in a buffer, yes.
Okay.
If your question is, can you have two completely separate vertex shaders that feed into the same geometry shader? I don't think so.
No, I mean, can I use the same thing I used in my vertex shader in my geometry shader?
Yeah. If you really wanted to do that, two vertex shaders into one geometry shader, use a separate pipeline, capture what one vertex shader says in a feedback buffer, and then pull a feedback buffer into your geometry shader.
Mm-hmm.
It can be done. It's just not the way that pipeline normally goes. Okay, so the tutorials here. If you go to the lighting arc here, there's a good set of lighting tutorials. I don't think they're quite as good as the other set of tutorials that I linked to in the class notes from last time, Wednesday, October, whatever it was. But they don't actually have code behind each of these tutorials in there. Eventually you get to the ones on these spheres over here, and they do have that code available. And so it has the lighting stuff that's produced during these things over here. And so if you read through these things, eventually you get to the code that we're about to go and disassemble. Okay, so that's where it comes from, and that's the kind of the reference for it. Okay, and so they have this thing set up, so if you click on it, it changes lighting models. And so you can kind of see a comparison of a few different ones there. And eventually they talk about transparent textures, which actually looks pretty cool, because you can see like the bottom side of Antarctica. Normally, if you want to see the bottom of Antarctica, you have to go explore Antarctic caves, which is probably more awesome, but this is more accessible. So Australia floats around down there. It's actually, that's the back of Australia. It's hard to see the front of it the way the demo is here. I don't remember if they got any other controls. Yeah, not really. No, you can't even go backwards. Okay, this is my son's favorite one. You can't really see it that well on a projector, but the water is actually slightly transparent. It's just mostly blue, and so you can kind of see through the world, like the whole thing is a blob of water with floating continents. Yeah.
What was the name of the wiki page that was on that one?
Well, I forgot, but I usually just say Wikibooks Modern OpenGL, and there you go. Yeah.
Can you please represent the world correctly?
Represent the world correctly.
It's not flat in that picture. I'm sorry.
Oh.
He's getting a lot of glare.
There's a project for you.
I never saw if that guy with the steam-powered rocket that was about to prove it was flat ever got off the ground.
I think he did, and he hurt himself.
Oh.
But he only made it like 1,000
My favorite,
Oh,
my favorite thing is the Earth is flat. You can see somebody really far out on the water. It's like that's because light bends with water.
I saw something not long ago, cracked me up. Someone talked about said flat Earth, and then showed a lamp, and it's like day, like everywhere on it, and then on a globe you can actually have day and night. It's like maybe just like simple things like that. It's like hard to imagine that the Earth is flat.
Yeah.
Like how would you have day and night cycle properly? Well, it's quite simple. The sun orbits.
Right. Well, it's difficult because the Earth is approximately flat. It just depends on your frame of reference. So this is the vertex shader, and it's really short because the lighting's taken care of in the fragment shader. But there's a few things we want to pull out of here. We haven't really talked about texture coordinates yet. Maybe we'll talk about texture coordinates on Monday. It's a very strong candidate for Monday, actually. So the texture coordinates are set up in here. Everybody from game design probably remembers the textures because we put textures onto things like brick walls and hand-drawn pictures, and it was great. But we haven't talked about it in this class yet. So the texture coordinates come in here. The vertex coordinates come in like normal. V chord up there is the same thing that we've been calling chord 3D and the other demos. Then we got the vertex normals in here for each vertex. And for a sphere, this makes total sense. Since it's supposed to be spherical, and they having each vertex have the coordinates instead of each face means that the vertex normal, the normal vector actually varies a bit over a single triangle. It's different in each corner, and then it's interpolated so that you get a blend of the corners anywhere inside it. Then we've got a position, and so this is a varying one in here. So this is a OpenGL pre-3.0 file, and so these days we call this an out vec4. I don't think that OpenGL will object if I change this to out. So we have an out vec4 position, and then we have an out here and an out there. And the attribute ones are all in. Okay, so the position is put out here, and this is the position in world space. It has that note. And we've also got the normal vector in world space again. So we're going to take something in model space, move it to world space. So I am going to grab a few of these. Here, I'm going to borrow this right here. Okay. I almost borrowed, this one has a sticker coming off. That's no good. That's different. This one does not have a sticker coming off. It's perfect. Okay. approximately right about full. Okay, let me see. It's slightly different shape. Oh well. Pretend that this is like this, it's just smaller, even though they're not exactly the same. So we got some model, and normally we have our model represented in usually around the origin, like 0, 0, 0 would be like kind of the inside of it. And it's in model space, so it's kind of the center of the world. So if this table here is our world, it's usually just sitting there right in the center. So what we actually wanted to draw was it like here. Then we have to apply a transformation to it. In this case, we want to do a translate in order to move it over, and we want to do a scale in order to make it smaller. And so we perform those two actions, and then it is over here, which is great. We could have applied a rotation to it as well. That would have been perfectly fine. Or a non-uniform scale or something like that. I think it kind of sort of looks like a uniform scale, although increasingly I keep noticing differences between this thing and that thing. For example, this is pointed a slightly different way. If we say it's pointed there, then they're more uniform. But I need to not get sucked into trying to make those things uniform. Okay, so we've got our matrix here, M, B, and P. So M takes our model and puts it into world space. Then B and P, they convert this into camera coordinates. So the thing is, if we're standing, oh here, we got a camera. So if we got the camera here, I can show you what the world here looks like that I was just setting up that you can't see. Looks like that. So if we've got this camera here, I'm holding the camera, and it has each of these two items in it, but the scaling is different based on the camera. Now, if we take the camera and we zoom in to this sanitizer bottle, then it's bigger, so it's been scaled up. So it takes up more space in the view. And of course, if we go out, then it gets smaller still. So that's important. And if we change the up vector on the camera, don't get sick if you're watching this, it changes as well where everything is. So we've got a number of transformations that take place based on the camera coordinates. Okay, so the camera is all done with V and P. We got to compute our viewpoint and our perspective, where we're looking at this whole thing from. Okay, now we calculate MVP right here. I will admit slight disagreement with this method. My concern here is we're passing M, V, and P, so we're passing in three matrices, and we're computing yet another matrix. So that means we're computing this matrix for every single vertex. So because we don't want to do this on the CPU once, we're doing it for every single vertex. And so if we've got like 10,000 vertices, then we're making a GPU do it 10,000 times instead of the CPU. GPU is fast, but it's not that fast. Anyway, regardless, it certainly works. Okay, so we got this MVP matrix like we've had before right there. Now we can calculate the position by just using the model matrix here and just doing our translation into a different world coordinate system. So that's happening, and then this position, it's an out vector 4, and so the whole reason to do this is so that in the fragment shader, we can figure out where the fragment was in the world. Like where is this fragment coming that we're about to determine the color of. Normally the fragment shader gets to be blissfully unaware of the world coordinates of whatever object generated the fragment that we're currently shading, but not if you're doing lighting. Okay, so then we got the varying normal direction. So what we do is we multiply the normal vector there, V normal, by the 3x3 inverse transpose matrix, which gives us a correct modification of the normals. Now, this stuff is only necessary if we've applied an uneven scale to the model. We were talking about that last time with that example where you take a ball and then you squash it flatter, and now the normal vectors are all messed up. Only happens if you're doing that kind of thing. I suppose you have to normalize them again if you're doing just plain a scale, yeah, so that's one way to do this. Okay, so then we got the normals and the position as both outs. Then there's the texture coordinates that we'll ignore, and then finally we calculate GL position exactly the same as we've been doing it. We take the position and multiply it by MVP. So that does that. Okay, so that's how this one works. Not a lot to be done because everything in the fragment shader is dreadfully complicated. Okay, so here's the fragment shader. We've got these things coming in. The varying things are actually in things in the new vernacular and OpenGL 3. What I didn't convert those. Okay. So we got our position and our varying normal direction, and we've still got our texture coordinates. And then we've also got M, V, and P back here. And we've got another uniform, the inverse of V. And then we have this, the texture stuff that we're not going to worry about yet. Okay, so in order to calculate a light, oh yeah, the V and the inverse of V is used later. Let's show you soon enough. Okay, so the lighting. Now, I haven't shown you this feature of GLSL very much, maybe not ever. And so with GLSL, you can take a structure like this in order to explain some input like this. And so we're going to have a light source, that's one of these, and it's going to be called light 0, and it's going to be a light source, and we're going to fill it out like this. And this is actually very much like C. With C, you can go ahead and make a structure like this, and there'd be no problem. In operating systems class, we've been identifying each of the members as we go down, saying the member, colon, what value it is. So we're doing the same thing in here. They just have to be in order. The light source is actually defined right here, hard-coded into the shader. That's not always typical. One thing that you might want to do is make it a uniform so that you can change what the lights look like from the C++ source code on the program. This doesn't support that. It'd be easy enough to do it. You just have to use a uniform for this instead. Okay, so our light 0 here has a position. It's got a diffuse component and a specular, the diffuse color and a specular color. And so the diffuse one is just the the directional light coming in and reflecting off in every direction. I'll make a quick explanation of diffuse and specular here because sometimes it can be hard to keep all of this straight. So suppose you got some kind of surface here. We'll say it looks like that. And you've got some kind of light over here. This is your light. And it's got light that's going to the surface. So it's coming in and it's hitting the surface. A lot of times these things are point sources. Let's try it as a point source. Change our opinion here. Okay. So you got some light and it comes in and hits this surface. So for a fragment, remember we're just dealing with one fragment at a time. Our big question here is what color is this fragment? That's what we're asking. Here, you can watch too. That's probably about right, although I can't quite see. Yeah, there you go. Okay. So the question here, what color is this fragment? And so the light's coming in and hitting it. Now, once it hits that fragment, the fragment is going to send light out in all directions. And so even back towards that. Okay. And that's what happens when you shine a light on something. If we take out light again, because they keep taking out light and using it for stuff. Okay, so if this thing were a perfect mirror, you wouldn't see the light. The light's going from a flashlight, and it should bounce up towards that corner of the room, right? And surely some of it is doing that, but you can also see the light on this piece of paper. So that's the diffuse component of the light. So it's, if you imagine it's like a laser, laser comes in here and then it scatters every direction. Laser pointers do that. If you shine your laser pointer at something, you can see it even if the laser isn't being reflected back into your eye. Okay, so that's diffuse. Okay, all this stuck together. Okay, then we got specular. And this is reflected light. So same kind of thing here. We draw a curved surface. We're dealing with some particular fragment. We just deal with our fragments one at a time. We got a light source, and it sends a ray that hits this. Okay. Let's move our light source just slightly. Okay. Sorry. Okay. And so then this surface is going to send out light, and the light is going to come and bounce off. So if you take the normal vector, This is the normal vector. And I'll call that Vn for normal vector. It's going to have the same angle on each side. Maybe I'll draw this again to make that maybe look more like it's correct. And so when you come in here with this angle, that's theta, and that's also theta. So they are the same. Okay, so think about a laser going in and then bouncing out. Now, it doesn't bounce out strictly like that. Like that's the center of the distribution, and that's the strongest point. But then there's less light coming out at angles to that. Okay, so it's kind of a, it falls off a bit. There's most light directly, and there's a little bit less that way. The reason is roughness. So if you take a surface, and the surface is a perfect mirror, and you're shining the light at it, the light will only go out this way. There won't be any scattered light from that. However, if your light surface is not a perfect mirror, suppose you have a glittery surface. Everything I can think of to give an example of a glittery surface belongs to my daughter. She likes to have her fingernails painted with various glittery stuff. And if you were to shine a light at it, it would bounce off the glitter, but it would also scatter as it bounced off. And you get some pattern kind of like this. Anyway, surfaces tend to do that. So if we take something like this, it's pretty strong reflection. You can see it there up there on the ceiling. And this one has a particular quirk that it reflects different wavelengths differently. I'll make it brighter so you can see better. There's some level of scattering. Anyway, the level of scattering is related to the roughness. This is Phong lighting here that we'll look at, and it has a term for the roughness of a surface. And so a rougher surface scatters light more. So if you have like a surface that's encrusted with glitter, it'll be rough and it'll scatter the light a lot. If you got something like a mirror, then it won't scatter it as much. The better the mirror is, the less it scatters. If you go to like a bathroom at a rest stop, a lot of times the mirror is a polished sheet of stainless steel, so it's hard to break. It'll scatter the light more than a mirror that's made with glass with reflective backing, like you might have in somewhere else. Okay, so you get this kind of thing. So the color and the brightness of this depends on where the camera is. If you set the camera over here, then you're going to get less reflection than if you set the camera over here. And so the specular light changes based on how close the camera is to this vector right here and how rough the surface is. If it's rougher, these will be larger, and this one won't be quite as big. It'll be more even across this, spread out over a wider area. Okay, so that's the difference between specular and diffuse. So the light here is actually the same color. It's a pure white, regardless of whether it's specular or diffuse. And then we got three values here for attenuation. And this is how fast the light drops off. So if you think about light dropping off, okay. Here. So there's a picture from underwater of a scuba diver next to a shipwreck. And so I'm hoping it'll give me a big version of the picture. Nah, that's fine. We'll do that. Okay. So you got this ship underwater, and you can see the front of the ship here fairly well, but back there, you really can't see it too well. And the reason is there's a great deal of attenuation in the water. The water is absorbing some of the light, and because it does that, it's difficult to see what was back there. Light is coming down, and we're getting a diffuse light from the top of the water. It's diffused almost to the point where it's like an ambient light. But the light that's reflected off of this railing back here is mostly attenuated before we get to this end. And so if you're rendering like an underwater scene involving like a shipwreck that divers are going to, this is going to be a really important point. You can see there the diver has a light, and it's making a dent, but not that much. The deeper the wreck is, the less light there is, of course, and that makes it more difficult. Oh, sorry. I forgot about that. It's hard to remember the telepresence here. Okay, so that's what the attenuation is. This is the wrong one. That's not what it meant to be. Okay, so that's what the attenuation's for, and it can be calculated 3 different ways here. You can have a constant attenuation. You can have a linear attenuation, stronger as you go further, or a quadratic that's even more so. And so this one just has linear attenuation and doesn't have the other ones. Okay, then we have the spotlight effect. So if you have a think about a spotlight in a theater. In a theater, a lot of stuff happens that the audience is not supposed to see, or at least, at the very least, not focus on. And so if the audience is not supposed to see something, then it's just not lighted, and then you can't see it. Pretty simple. So they have a spotlight that cuts off abruptly at an edge and gives you a particular lighted spot. Okay, so we got an angle here where we cut off the spot completely. Okay. So that can give us a particular radius of light here. This one's very broad angle here. It's cut off at 108. Okay, now we have a direction, and this seems to be set to nothing at all. And so we're not really using that feature. Okay, so we got light 1, light 0 set up that way. You can set up more lights. In OpenGL 1 point whatever, you get a strict limit on how many lights you can have. Usually it was like 8 lights or something like that. Since you're setting all this stuff up yourself in OpenGL these days, the limit to how many lights is how many lights you want to have and how fast your GPU can handle all this stuff. If you decide that you want 462 lights, then your fragment shader is going to take a while to run, and that might not be okay. Okay. What it will do is limit the maximum resolution. Remember, you get fragments that correlate with pixels. And so if your fragment shader takes a really long time to run and your frame rate is horrible, just lower the resolution. At some point, the resolution will be low enough, there's not that many fragments, and so everything gets shaded fairly quickly. If each fragment can have its own compute unit, you're going to have good frame rate. It might happen at 320 by 240 resolution, but it happened. They don't laugh too much at that resolution. We used to use that resolution in the old days. Okay. Okay, so then we have a material, and so the material is all, we have seen ambient light here too. So the ambient light is really simple. It's not associated with a particular light source in this demo, although you could make it associated with a light source if you wanted to. You just have to apply it, for each light source. It doesn't make a lot of sense to associate with a light source unless you, for example, had a bunch of lights and you're going to be turning them on and off, and you want the ambient light to increase depending on which lights are on and off. You can put a component with each of them. That seems a little strange. Anyway, it's just set up as a separate ambient light here. Okay, then you got a material. And so the material is set up with 3 colors and a shininess. And so this is way more complicated than just like a red, a green, and a blue thing. And the reason is just when you reflect light off it, a lot of times the specular color is in fact different than the diffuse color. A lot of times the ambient and the diffuse colors are the same. And so it's really popular to have the first 2 actually be the same. I think I gave a demo last time where I took something like probably the chair. I keep picking on a chair for video stuff since it's sitting here. And so you can see it's like a dark red, but up here in the projector it's kind of a lighter color. And if I make a really bright spot, you can see it kind of tends to be almost like a whiter color and less red under the intense light. And so things commonly sort of change their color there. I should have worn a shirt that had an actual color. I wasn't thinking. Okay, here's something that this should have that property. Okay, it's green, right? That's the color. So when we shine an intense light on it, though, you get kind of a whiter sort of look there. Especially here, I'll turn it down. So if it reflects kind of in your direction to some extent, trying to shine a light in everybody's eyes, you can see the white nature of it gets stronger. I'm sure everybody's at some point been behind a car in traffic that was like red, and when the sun shines off the trunk and hits you in the eyes, it's like white. Okay, so that's the specular nature. Yeah, I've seen spots too after that demo. Okay, so that's why we have a different color here. So you can see on this one, the specular color, when the light bounces off it, is just white. But it's got a color to it for diffuse and, well, not ambient. Ambient's actually white too. Now this demo here shows texturing, and so I don't know if this material is actually even used. I think it's added on to the texture color is the way they use it. Oh, and you got a shininess, and it has to do with how much of the light is reflected back off, like what is the degree of specular lighting that you get. Okay, so that introduces what these things are. So in terms of grabbing this demo and using it, which was what I intended to do today, but probably I'm not going to have time to do, you just have to make all of this stuff happen. And if we excise the texture from it, then we won't need that part. And so if we pull all that stuff off, then we can go ahead and use this fragment shader with something else, provided we give it an individual M, V, and P, and the inverse of V, and for the vertex shader that matches, the 3x3 inverse transpose. So you give it all these things that we don't normally give these shaders, and then it should work. Well, hopefully you can do that. Okay, the normal direction is not actually normalized in the vertex shader, and so we normalize it here. I'm not sure what the justification is for normalize. Oh, I know what it is. After you interpolate it over the triangle, you might not get a unit vector. Because if you interpolated it between two vectors that are different, it's not guaranteed that the interpolation won't leave it something other than normalized. I believe that's the reason. Okay, so anyway, that's we got to get the normal direction there normalized from this one that's not necessarily normalized. And then we got to get the view direction. And up here in this view direction, what we're taking is the inverse of the V matrix, and we're actually giving it a vector of basically nothing, and subtracting our position from the result there. So these things will pop in later. They'll make a lot more sense when we go look at that. This part here is relating to texture coordinates, so we won't worry about that one. That's figuring out the texture color. And again, we're not going to look at the texture coordinates right now. So what we're building up towards, we're going to build backwards from this a little bit. Eventually we have to say GL frag color down here and say what color our fragment is. That's the question we've been trying to answer the whole time. What's this color, fragment's color? So we're going to take the ambient lighting color and the diffuse color and the specular, the color from there, and that gives us our color. And then it's got to be a vec4, so the 1 down there is just setting transparency of this particular fragment. Okay, so in order to do that, that's all we need. We need ambient, diffuse, and specular colors. So the ambient is from right up here. We're saying vec3 ambient lighting is the scene ambient times the color. In this case, the texture color. Scene ambient, it's mentioned there, but then that's coming from right up here. We got the scene ambient lighting, and so it's being multiplied by the color that we're getting from the texture. When you do the texture, you take basically a picture and stretch it over your 3D object, and so then you can take the color out of the picture in order to use for the texture color. So this would be the same thing we've been passing through as like F color or whatnot. So we have like F color or whatnot times the ambient lighting, which in this case is pretty weak, and it's usually pretty weak, and that gives us that. Okay, so that component there was really easy. Then we got the diffuse reflection, and so the diffuse reflection up here, we have to take into account the attenuation, and so if you scroll, if I scroll up here. We got this float attenuation up here. So if we track the progress of this attenuation, if you're looking to see if it's a directional light, 1 is no attenuation whatsoever. But if we're looking at a point light or a spotlight or some other kind, then it's different. So up here we have this light's position W, and I sort of ignored it. We got a 1 here at the end. The W is actually hijacked to indicate what type it is. And it's suggesting to somebody that they could hijack W for some other purpose in lab. I forget who and for what purpose. Okay. Yeah, anyway, it's kind of a common thing to do, to take this W and hijack it, since the video card passes a VEC4 anyway. But in here, in this case, it's being used for the type of light. So you can have a directional light, or you can have a point or spotlight, or other kind of light. Okay, so if it's a directional light, which is just kind of like a laser here, we just go ahead and set this to 0. Now, a point light is still directional in the sense it's coming from somewhere, same with the spotlight, but we have to do more work on the attenuation because the light's going to spread. I haven't really talked about ones that are purely directional like a laser yet, and actually they're basically more simple to compute anyway. The attenuation here is going to get set depending on what's happening here. So there's a spot cutoff. And we were talking about the spotlights a minute ago, and I showed you that this one's like really pretty wide, 180 degrees. And so this is not really like a spotlight. It's like the opposite of a spotlight. We're looking at a floodlight. But either way, we got some kind of spot and some kind of cutoff. And this cutoff is at 180 degrees. So if we're outside of the spotlight cone here, then attenuation is 0, like we got nothing left. Otherwise, the attenuation is multiplied by the cosine here multiplied by the spot exponent. So the clamped cosine, we're taking the clamped cosine, and this is the maximum of 0 and the dot product of the light direction. Now, I think I talked about last time how you can use a dot product to do the same thing as you do with a cosine. And so that's exactly what's going on here. The dot product is larger if the two directions agree, and smaller, all the way down to 0, if they are perpendicular. We're going to need cosine of the angle that the light's coming in at, and so the attenuation might be set much higher, depending. Okay, so once the attenuation is set, the initial attenuation right here. Okay, so the initial attenuation, we take 1 and we divide it by, this is a quadratic equation here. You can see we have distance squared here. There's distance, there's no distance. And so we can actually write this in the normal form for a quadratic equation. I know you don't remember when you learned quadratic equations. I also learned these in grade school, and I also thought they were fun.
Quadratic equations are learned in algebra.
Algebra, okay. So we've got this thing, distance here, d. And we've got d and a d squared term, and we've got some addition going on right here. And so we've got, here's the constant attenuation plus the linear attenuation times d, and then we've got the quadratic attenuation times d squared. And so we take 1.0 over that whole thing there, and that's our attenuation. And so that's the plan. So it's a quadratic equation. They are back from algebra. I'm sure you thought you'd never see one again, but there they are. And in fact, if you're watching the video, you can see some great specular highlighting from the light bouncing off the board there. Okay. Sorry, I might have messed that up slightly.
I can fix it.
Okay, so there's what we're looking. Okay, so there's what we got for attenuation here. Okay, so the attenuation set using these factors there, and then after that we look at this how we decrease it with this spotlight. Now it's not strictly attenuation here, although it says attenuation, and that's the name of the variable. Up here we're using it as attenuation, like how much light has fallen off. Here we're using attenuation like we're going to turn off the light if we're outside the range of the light. So we're kind of using it to mean two things here at the same time. Okay. So the attenuation is, there we go. I think that's covers attenuation. Talked about that one for a long time. Okay. So then we look at the diffuse light and the texture color. And multiplying these colors together here is giving us an intensity for it. So the texture color, we're kind of ignoring the material color. But this is it's the color of the material under diffuse light. And I realize this was set up here in a structure right there. I don't think we're really using that. The material, it's mentioned these three places. That's it. You see it's completely ignored in the rest of the file. Okay. So that's because it's using the textures here. But when we take the textures back out, we'll put the materials diffuse component right here. Okay, so we got the color there for the diffuse light, and then we've got the maximum of 0 in the dot product of the normal direction and the light direction. So if they're perpendicular to each other, we'll get a dot product of 0, and we won't see any light. Now this max here is to avoid negative light, because if our light source is behind the thing that we're looking at, you know, here, this sort of situation. So suppose we got our handy chair here again, and we've got our light, and you know, the light's here. But let's say we take this light angle and we make it like that. Well, now you can't see anything, right? But it's not like a negative light. I mean, this flashlight here isn't going to like suck the light out of the chair from the projector and eat it or something. So we have to prevent that. And we start to get a negative with the actual cosine. So if we say maximum of 0 in this, then we're guaranteed to never have negative light. Okay.
Oh, I like negative light.
Well, you can have negative light if you want to. I mean, you can have a game where there's like the light cannon, and it removes all the light from the room so nobody can see. Ooh, maybe the light grenade. You do the light grenade, all the light gets like sucked into it.
I like it.
Yeah, I mean, if you're dying, you just like throw the light grenade. Nobody can see anything and you escape.
There's a anti-light material, which is the darkest material I think they know, because it just really absorbs light.
Yeah, it will. But you can't use it as like a light ray to absorb light that's somewhere like not headed for it.
It's more like a dark ray.
Yeah. Okay, so this is cut out that part. So that gets our diffuse. It says diffuse reflection here. The light is in fact reflecting. It's just that it's reflecting to all directions, so it's a diffuse sort, like the diffuse we drew over there. And that gives you the diffuse reflection. Okay. So then lastly, we've got the specular reflection. Because how could we ever be done with these lighting calculations? Okay. So the specular reflection here, we look at the where the light source is. So if the dot product gives us like a 0, then again we're about to have negative light, so let's not do that. Okay, so well, it's on the wrong side. You know what? That's the wrong interpretation of it. I'm sorry. Forget I said that. Okay. So we'll look at what side of the we've got this on. Okay. Now I was just backwards. This is like no light for specular. So this is the one where we're on the wrong side. This is the one where we're on the right side. So I said that exactly backwards. Okay, so if the light is behind us, again, we just do 0, same kind of thing we did up there. But if we're on the correct side, then we'll go ahead and actually calculate what we're looking at in terms of light. Most of this looks pretty similar. We got the attenuation. We calculated the attenuation exactly the same way as for the diffuse light. And then we're looking at the specular component of the light. And we're actually using the material here this time, finally.
Front material.
Yeah, it's called front material, though. Is front material somewhere else?
Yeah, they do material, front material is equal to.
Yeah, but it's just down here. So we are actually using the material definition for specular, but we're not using the diffuse material currently. Okay, that's fine. I want to be a little higher there. I think we're starting to be hard to see. There we go. Okay. So we got the specular color of the light. We got the color that the material turns it as it reflects off of it. And then we've got some texture coloring there that we won't worry about too much. And then we've got this equation where we figure out how much is actually reflected towards the viewer. Okay, Long term. Okay, oh my, shoot. Okay, so there's a Phong term that's embedded inside that thing, and if we pick it out, then it will make it easier to see. There's a diagram, kind of like I've been showing. It's got this like disembodied eye instead of a camera, but you know, same kind of thing. But eventually what we get to is a Phong term, which I might have just scrolled past it here because I was expecting it to be labeled perhaps more. Okay. So eventually we got a you know, amount that's reflected here, and I want a simpler Phong term explanation. You should read the Wikipedia one, or we might just go back and get it out of this thing. It's we're about to run out of it. Here, this is a good one. There, that's the font term. That's more what I wanted to show you. I didn't want it to have too many things in it. Okay, so we just take the dot product of the two vectors involved here. We got a direction of the light goes and reflects, and we've got an offset of that to the camera. What we're looking at is the angle between the view direction, that's what the camera is, where the camera is coming from, and the direction of perfect reflection. So if you take this right here, and you take this as the angle of perfect reflection, and you have a camera over here, and so what you got is a direction the camera's kind of looking at it from. This angle right there is what we're interested in. How far off are we from where the light would just like bounce right back into our eyes? If you go into the bathroom and you shine a laser pointer and you shine it into your eye, that would be this kind of your eye is lined right up with the direction of perfect reflection. Don't try that. It has a little warning on the laser pointer that says not to. And if your laser pointer is one of the ones that pops balloons, really, really don't do that. Okay. But if your surface is scattering the light a bit, then you'll still see some even if you're outside of it. So then the Phong term has this exponent here, s. And so s is approximately the roughness of the surface. You have a rougher surface. You have, I guess, a higher surface. S term represents the roughness of the surface. A smooth surface, which should have a smaller highlight, has a large s. Yeah, there you go. Okay. Large exponent makes for a small highlight, not very much light scattering. Okay. Specular exponent can range from 0 to infinity. And in some ways, this is a good model for the real world. You can't polish a surface perfect. You can't get a high enough exponent to make the reflection perfect. Anyway. Okay, so that's the Phong term. Okay, so V dot R. So if you look over here, we've got a reflection taking place here where we reflect a vector in order to calculate that V vector going on right here. And then we've got a view direction. So reflect is actually a GLSL function. Okay. And for a, this we call reflect here, and you've got an incident vector and a normal vector. So for a given incident vector I coming in and a surface normal R, you reflect it back the other direction. Basically, you make this one right there, the red one. Okay. Or was the red the normal? No, the normal one's the blue one. Yeah, so you make the red one. Okay, so it's got a function in here built in to get that. So you get that one, take the dot product with the view direction, and that's what the Phong term said. And then you raise it to the shininess. So we take the maximum of the, we again clamp this to 0, so we won't have any negative light here. And so then we take the power of it raised to the shininess, or roughness, or smoothness. We've called it all three of these things now. And that's the exponent for the Phong term. We've got the, so this whole thing down here represents the Phong term that we multiply this whole thing by, and we get the specular reflection. So that's the last component in here, the specular reflection. Add those together, and we get the actual color that the fragment ought to be given the presence of light 0. So that's lighting. Okay, very different explanation than you would have had in OpenGL 1 from the game development class. So if you've had both, then hopefully it wasn't boring the second time.
Slightly different.
Yeah. It kind of has the same things, ambient and diffuse and specular, but it's...
Did everything in game design, did we just have it generate its own light or something like that?
No, we put a light in there. But OpenGL 1 handled the lighting kind of automatically.
Yeah.
And so we didn't go through and code it ourselves. And, well, we didn't code this, we downloaded the demo.
Well, like everything that we put into the game, I remember it all had kind of like a glow to it, which was kind of weird. I always thought, because there's no discernible place to light where our light source is coming from.
Yeah, it had one in there. Main.cpp. Okay. Okay, so we had a light and I had a position and we had it enabled. I think we had I thought we had a second light in here. Yeah, we also have light 1, which is way up high. And so light 1 is kind of shining down on everything.
Yeah. Was our ambient light pretty high too then? Is that like
Yeah, I think our ambient light was kind of high. The light 1 color. Yeah, it's actually, so ambient and diffuse are both set to half, half, and half,
Yeah.
which is a lot. And so the ambient makes a big component of this. And actually the same thing happens on the other ones. Ambient is set very high.
Like I remember, even if you glitched inside of one of the boxes, you know, you had that like you weren't supposed to be able to get into everything glowing inside.
Yeah.
Which is kind of really weird.
Yep.
We didn't have anything that blocked light.
I thought we tried to.
Well, you can't block the ambient light though.
Yeah. That was very good.
Yeah. Oh, that's right. I did that for my other class.
Huh?
Oh, it's all rendered to wireframe. Okay, I guess I gotta be done here too. I was gonna go and there it is. Still polygon mode.
Is he fucking?
Yeah. I think the ambient's so high it kind of washes out everything else.
Yeah.
Basically.
Is it? See, there was the weird thing was there was shadow effects on the
Well, the funny thing is, there's not shadow. It's either like not normally.
yeah.
And the shadows are an entirely different piece of the puzzle to add. The lighting I just showed you doesn't have any shadows.
I think some people
Oh,
added
you're inside
shadow.
one of the blocks now. Yeah, you slipped
Even
inside.
on the
Oh,
inside
I'm
of the
stuck
block. Yeah.
inside it.
Yep. That happened to me a lot.
I hate it when I get stuck in a staircase.
That's why I made the blocks so small for my platformers, because I'm like, okay, there's no way now you're gonna get